previous slides. That's exactly what we calculated here for our equilibrium constant expression. So that K sub F is less than, really, this is equal to K sub C. So for this reaction, we say K sub R. Hang on. All right. So should K sub C be greater than or equal to or less than 1? We got less than 1. Yes. So if that's true, K sub C is less than 1. Everyone see that? All right. That's going to be important because it's going to tell us, as we'll see, if our reaction is reactant favored or product favored. We'll get to that in a little bit, but that is a calculation that's important, an estimation that's important. All right, so let's look at another example. Let's take carbon monoxide and hydrogen gas and combine them to form methane and water. Everything's in the gas phase. There's going to be an equilibrium that's achieved. But what we're going to start with is 3 moles of H2 and 1 mole of CO, carbon monoxide. And so what we'll see is that initially our moles of H2 will decrease. So this we have, can you see that? Yeah, moles of substance on our y-axis and time on our x-axis. So the moles of H2 are going to decrease, as you would expect, because they're reacting to form products. Moles of CO also decreases for the same reason. And the moles of CH4 and H2O are increasing with time because we're forming products. So after a certain point, and you can kind of eyeball this, maybe this point in time, the concentrations of reactants and products are no longer changing. I'll put in brackets. Concentration of reactants and concentration of products are no longer changing. So that means we've achieved equilibrium. And what is our equilibrium constant expression for this? We don't need to actually calculate values, although you could from the plot if you assumed you had 1 liter. But we're not going to go there. So K sub C is going to be equal to the concentration of CH4 times the concentration of H2O divided by the concentration of CO times the concentration of H2. What do I do with that? H2? Concentration's got to be cubed. Yeah. So again, we take our stoichiometric coefficients, and those are the powers in our expression, the exponents. Questions on that? Yes? Can you find the order of the reaction from the exponents? No, this is a different thing. The only way you can do that, at least in terms of what we're going to see, is from knowing you have an elementary reaction and then using stoichiometry. But we probably won't be doing too much more of that specifically in this chapter. Okay. So remember I told you about Haber and how his Wikipedia page is fun? This is Fritz Haber. Okay? The Haber process is one of the most important chemical reactions that we use in society. It seems a little extreme, but it really is true, because this process of taking nitrogen from the atmosphere and hydrogen from the atmosphere and reacting them to form ammonia is incredibly important for agriculture. And it was incredibly important when Fritz came up with this reaction during World War I, when Germany, country he was from, needed to develop explosives. And their supply of fixed nitrogen that you can use in some way, it's not in the atmosphere, was from, I think it was Chile, and their supply got cut off. And so they needed a way to come up with fixed nitrogen. And so this process is what sort of was developed. You might also see it called the Haber-Bosch process. I think that's how you spell that. Bosch was the person who made this reaction happen on the industrial scale. Okay. So let's look at our reaction for the formation of ammonia, our equilibrium. And let's say that at equilibrium, we take a sample of whatever container we're reacting in, and we find that we have 0.3 moles per liter of nitrogen, 0.9 moles per liter of hydrogen, and 1.4 moles per liter of ammonia. We can use those values and calculate K sub C at whatever temperature this was. So K sub C is specific to a temperature. Okay? So what we can do is simply plug these values in to our K sub C expression. So we'll have K sub C is equal to our ammonia concentration squared. So it's 1.4 squared, divided by nitrogen concentration, 0.30, and our hydrogen concentration, 0.90 cubed. Okay. When you multiply and divide and square and cube and all that stuff, you do your algebra, you should end up with a K sub C value of 8.96. Okay. Couple of things here. The Kc values, equilibrium constants, Kc or Kp, these are going to be unitless numbers. So you can be sloppy with your units here. And one of the reasons is just simply that if you were to actually do the unit analysis on a number of these reactions, you would end up with crazy units. They would be meaningless. So we leave it as a unitless value. The other thing is that, and as we'll see, when the equilibrium constant expression is greater than 1, that means that the reaction is product favored. And we're going to go back to this. This is jumping ahead a little bit. Okay. If it were less than 1, it would mean that reactants are favored. And the way you can think about that mathematically is that the denominator, which has the products in it, is a greater number than the reactants, which has the numerator, which has the products in it, has a greater value, so thereby giving a number greater than 1 than the denominator, which has the reactants in it. Okay. Questions on that? So this is from the previous slide. K sub C at this temperature was 8.96. Let's say we redid the reaction. Maybe we started with different concentrations of reactants, and we end up with, at equilibrium, N2 is 0.6 moles per liter, H2 is 1.8 moles per liter. Let's calculate the concentration of ammonia. I'll let you guys do that. So you can use this K sub C value because it's from the same temperature. But calculate the concentration of ammonia. And feel free to talk to your neighbors. Go ahead. Sorry. How's it going? Doing good? How's everyone up here? Anyone have questions on anything? Doing all right? Everyone doing all right down here? Any questions? Questions? Questions about anything? Questions? You guys doing all right? All right. All right, so hopefully you came up with a value for the ammonia concentration. Does anyone want to offer a number, an answer? What'd you get? 5.60? Yep, that's what I got. So let's kind of make sure we're all on the same page here. I'm going to rearrange my equilibrium constant expression to solve for NH3. So basically I'm going to multiply both sides of the expression by what's in the denominator, and then I'm going to take the square root. And I'll end up with K sub C times N2 times the concentration of H2 cubed divided by nothing. Sorry. Yep. And then take the square root of that. Cool. And hopefully we get 5.6. Questions on that? Okay. So let's keep up with our doing our algebra here, and let's do something where we simply reverse the reaction. So we had our N2, our nitrogen and our hydrogen reacting to form ammonia, but now we're going to reverse the reaction. We're going to start with ammonia, and we're going to produce our nitrogen and our hydrogen. We still end up with an equilibrium, but now we sort of flip the definition. Okay? So in doing so, we should end up with a K value, and in this case, we're using K prime to signify we've reversed the reaction. And we still have products over reactants, so it's N2 times H2 cubed divided by NH3 squared. Okay. What would you expect K sub C to be? Same? Not quite. So, I'm sorry, K sub C, yes, is 8.96. I asked the wrong question. What is K prime? Yep. We take the inverse. 1 over 8.96. And it's simply because we've taken the inverse of our equilibrium constant expression. And so, hang on. Let's do this. Ignore that. I ended up changing the concentrations and I forgot that I did that. So, but this would give you the answer if you're using the concentrations in the first slide we talked about. So I apologize for that. Yeah. Questions? Okay. So if you reverse the reaction, K prime, the new equilibrium constant for the reversed reaction is 1 over what it was for the opposite. So we can write K prime equals 1 over Kc. Question. Okay. I think with the last concentrations we should have ended up with, is this a whole different reaction? How confused am I? That's a great new thing here. New reaction, new equilibrium. Oops. Okay, so now we have N2O4 in equilibrium with 2 NO. So this is the reverse reaction of that one that I showed you with the brown gases, the bottles. And we are going to tell you that the K sub C for this is equal to 0.212. I think it's actually 0.211. Okay. And the reason I'm telling you that is this is based off of a problem in your book where the concentration of NO2 is 0.0172 and the concentration of N2O4 is 0.0014. Okay. So we're going to need to work with these. So if you plug these concentrations in to this equilibrium expression and solve, you should get 0.211 for the value of K sub C. So if we reverse that reaction, okay, we just saw what we would get. It's 1 over our K sub C value. So it's 1 over 0.211. You should end up with 4.72. Okay. But what happens if you multiply the reaction by 2? So now we're going back to our original reaction where our equilibrium constant was 0.211, and we're going to multiply that equation by 2. We'll end up with 2 N2O4 in equilibrium with 4 NO2. What do you expect to happen to the equilibrium constant? Well, let's write out our equilibrium constant expression. I'm going to call this Km for multiply. And this is going to be equal to the concentration of NO2 raised to the 4th power divided by the concentration of N2O4 squared. Everyone see that? And so, what is this? This is actually the original K sub C squared. So K sub C was NO2 squared over N2O4. And so if we square that whole thing, we should get our new value for K sub M. All right. And then what would you expect to happen if instead of multiplying the reaction by 2, we multiply by 3? It's going to be Kc cubed, all right? So when we have a K that's multiplied, it's going to be the original Kc value raised to whatever factor it's multiplied by. All right? Fun. What if you half a reaction? Square root, yeah. So same sort of thing. If you half a reaction, you're essentially multiplying by 1/2. So K1/2 is equal to, we could say, a square root of K sub C, or K sub C raised to the 1/2. Cool. All right. Let's do a new problem. We've got where we have a 2-step mechanism that forms an overall reaction. And we want to know the equilibrium constant for the overall. But let's say we have, for step 1 of our reaction, carbon monoxide plus 3 hydrogen in equilibrium with methane, CH4, and water in the gas phase. We know that the equilibrium constant from we've done some experiment, and we know that the equilibrium constant for this reaction is 3.92. This reaction then is just step 1. So step 2, we're going to take methane plus 2H2S in equilibrium with CS2 and H2. One thing I'm going to do here, just to simplify later on, I'm going to call the equilibrium constant from step 1 K sub 1, and the equilibrium constant from step 2 K sub 2. And this is a huge number for step 2. It's 3.3 times 10 to the 4. Oops. You see that? Yeah. Okay. Let's say we add these reactions together. Our methane is going to cancel. We've got, you know what, I missed this stoichiometric coefficient here. This should be 4 hydrogen here in the product side of step 2. So 3 of the hydrogen on the reactant side of step 1 are going to react with 3 of the hydrogen on the product side of step 2. Okay, and so our overall equation reaction will be CO gas plus 2H2S in equilibrium with H2O plus CS2 and H2 gas. Everyone okay with that? Okay. So what is the K value for this overall reaction? Let's first start by writing the equilibrium constant expression for the overall, just simply using the concentrations of reactants and products. K overall is going to be equal to the concentration of H2O times the concentration of CS2 times the concentration of H2 divided by the concentration of CO times the concentration of H2S squared. So the cool thing that happens is that if you take the equilibrium constant expression from step 1, and you multiply it by step 2, hang on here, you should end up with K overall. And we can prove that by simply writing our equilibrium constant expressions for K1 and K2 and showing that multiplication forms our K overall. So K1 is going to be the concentration of CH4 times the concentration of H2O divided by the concentration of CO times the concentration of H2 cubed. I'm going to put that in parentheses for K1. K2 is going to be the concentration of CS2 times the concentration of H2 raised to the power of 4 divided by concentration of CH4 times the concentration of H2S squared. All right. And now we can simply cross things out when they're going to cancel. So CH4 is going to cancel. 3 of our H2s are going to cancel in the denominator with 3 of the 4 in the numerator. So that goes to 1. And so we're left with H2O times CS2 times H2 in the numerator, and that checks out up here, and CO and H2S squared in the denominator. Yeah. Cool. Questions on that? Yes?
If there were 3 steps, it says can you just multiply them?
Yep. If there's 3 steps, you can multiply another one, another K value. So we could actually calculate what this value is. And so K overall will be the 3.92 from step 1 times the 3.3 times 10 to the 4th from step 2. And get 1.3 times 10 to the 5th. Yeah. Other questions? Cool. I think we're done. You guys have had a long week already.
Question on, I guess, where we are in the classroom.
What's that? I couldn't hear you.
On the, I've already forgotten the name, on master, it says that we have the 5.5.2 reading on Friday. I'm guessing without that knowledge, I guess we should be reading on Friday.
Oh, 5.1, 5.2, maybe 5.3.
Okay.
Yeah. I didn't want to give you guys a reading for today. That's not fair to you. You guys took an exam and ended at what, 7:15. So yeah, I wasn't gonna assign a reading or homework for today for that reason.
Gotcha.
So we just took a day off.
That sounds nice.
Yeah. Yep. No problem.
Hi.
Hello.
I sent you an email last night, but I'm sure you probably haven't seen it yet. I took the iPad or the exam on the iPad